Hello everyone, I am Dipen Opani, final year in-service civil student from College of Science and Technology with the following member from final year civil. We would like to demonstrate the model that has been prepared as a part of earthquake engineering module for our final semester. Next, we'll have Mr. Sishir Subedi, who would be presenting on the material used, method of construction, principle, and the technical message it conveys. Finally, we'll have Ms. Tambar, who would be completing our presentation.
Hi everyone, I'm Mr. Subedi, and let us continue with our presentation. First of all, let us talk about the materials that has been used for the construction of the model.
These are some of the materials and apparatuses used in the construction of our model. Plywood is used for the construction of the shake table. The shake table is an instrument which is used to induce experimental earthquake for testing purpose. Polymers and timber are used for constructing the structural members such as beams and columns. Steel is used to make diagonal braces as well as for binding the beams and columns together. Paper is used for constructing the slab. Drill machine is used to provide power and drive the shake table, and lastly, stone is used as a pendulum.
Now that we have seen the materials that has been used in the construction of the model, let us look at the principle, the working mechanism that drives the model, and the demonstration of the model.
For the first case, we have behavior of structures during low frequency oscillation under self-weight. A tall building will respond to a low frequency oscillation. The structures in this demonstration are behaving to the oscillation under self-weight. Let us see the live demonstration through our model. For case 2, we have behavior of structures during high frequency oscillation under self-weight. In this scenario, a short building will respond to a higher frequency oscillation. Let us see how the live demonstration showcases this phenomena. For the next case, we will be looking at the addition of diagonal braces to minimize the lateral displacement of the structure. Diagonal braces act as lateral force resisting systems in high-rise buildings by withstanding the tension forces. As we had seen in the earlier demonstrations, the tall structure has noticeable lateral displacement. Let us see how this can be fixed by adding diagonal braces to the structure. For case number 4, we'll look at the addition of load to demonstrate mass irregularity. When the weight of a floor is double or more than 200% of the weight of its adjacent floors, there can be phenomenon of mass irregularity. This could lead to reduction in ductility and enhancement of P delta effect. In this demonstration, we have placed a mass at the uppermost floor, making the scenario more critical. Let us see how the structure behaves in this case. For the final case, we will be looking at the damping mechanism using pendulum power. One of the damping methods that can be implemented is known as the pendulum power, used primarily in skyscrapers and high-rise buildings. Engineers suspend a large ball with steel cables with a system of hydraulics at the top of the buildings. When the building begins to sway, the ball acts as a pendulum and moves in the opposite direction to stabilize the oscillation. Like damping, these features are tuned to match and counteract the building's frequency in the event of an earthquake. As you might have noticed that we had placed a mobile phone on top of each building in cases 1 and 2. This was done to record the acceleration of the building in the horizontal direction along the x-axis using an app called iDynamic. Although the acceleration of the building is very high compared to a real-life earthquake scenario, we still did it in order to compare the situation of the building in case of bracing and without the bracing. And as you can see here, that the building with bracing has lower acceleration of the building compared to the one without the bracing. Similarly, in the shorter building, we can notice that the acceleration of the building is higher in the one without the bracing, and it is much lesser when a bracing is added. So from this we can conclude that the acceleration of the building drastically reduces when a bracing element is added to the structure, thus reducing the lateral displacement. Now let us look at some of the outcomes that we have learned from these experiments. Firstly, the behavior of structures to different frequencies of oscillations depends on the height of the structure. The seismic weight of the floors should be uniform in order to have neutral center of gravity of a building and ultimately avoid mass irregularity. Since most structures do not resist lateral forces of earthquakes, it is recommended to add diagonal braces and moment frames to avoid lateral displacement. And lastly, pendulum power damping could be used as an alternative in high-rise buildings and skyscrapers in order to reduce the frequency of the structure during an earthquake.
To conclude, we could learn that the shake table mechanism performs well in providing us the information about how the structures are going to behave under time-varying seismic force. For this, we would like to thank our module tutor, Center of Disaster Risk Reduction and Community Development Studies for funding our project, and the college management for their timely help during the execution of this project. Thank you so much for watching.